Going over more demos, new and exciting demos that you have never seen before. And I'm going to prove to you that you do not know Newton's first law the way you think you do. All right, Mr. I know Newton. Sure, I had a fig Newton before I came here. All right.
I was friends with Newton.
Now, okay, Josh seems to think that he knows everything about Newton's first law that needs to be known. So, I look at this one. You did this yesterday. Did you get to do this yesterday, Josh?
Yeah.
The toilet paper? All right.
How did it work, Josh?
All right. Very good. All right. Thank you for not, all right, so I pull this slow.
I think I got this one.
And what happens? What happens?
It doesn't rip.
It doesn't rip. It keeps rolling. Okay. Now, what, Josh, is Newton's first law?
It's an object stays in motion until it acted, or at rest until it's acted on.
All right, great. Is this an object in motion? Is it in motion or at rest? Right now.
Well, actually, it's moving.
Right now. Right now.
It's a rest, Josh.
Motion or rest?
You think?
Yeah, wait. Show of hands. Motion or at rest? Is this at rest right now?
Whoa!
Okay, good. So, an object at rest wants to do what?
Stay at rest.
An object at rest wants to do what?
Stay at rest.
An object at rest wants to do what?
Stay at rest.
An object at rest wants to do what?
Stay at rest.
And there you go.
Toilet paper.
There you go.
God, I need that.
All right, so now, so it's pretty obvious, right? It was clean. It's never been used. All right, so now my question is: here is a mass.
It's a mess.
It's a mass. I have a string. The strings are, to all practical purposes, identical. Now, if I take this mass and I hang this mass on this string,
Now you have a mass.
now I have a mass on a string.
Train
Our masses are touching.
Okay.
Everybody watch Mr. Newton. He's trying.
Do you?
And I realized that
All right.
everyone was wrong.
You ready? Hey, here we go. So, now, is this object in motion or at rest?
At
And
rest.
rest.
So, if I try to pull really, really hard down on the string, what will the mass want to do?
Drop.
It wants to stay at rest, because an object at rest.
What if you pull it?
Huh?
Stay at rest.
An object at rest. So, okay, so we got questions. He says at rest, she says in motion.
It'll
Now,
run.
okay, so I'm going to pull on this, Allie. I'm going to pull the string real hard, real fast. The string is going to break somewhere. Will it break up here or down here?
Down there.
Will it break above the mass or below the mass?
Well, let's find out.
I want to know, how many people think it will break way up here? Raise your hand.
I don't even care.
How many people think it'll break way down here? Raise your hand. Why would you think, let's go with Josh, why would you think that it would break on the bottom string and not the top
I don't
string?
see where it's attached.
That thing.
Is he pulling it harder?
I don't know. Maybe the mass will act like a force as you're pulling the hand, and you're trying to apply a bigger force.
The mass has what property?
Inertia.
And inertia states that an object which is
Not rest.
wants to what?
Stay at rest.
Stay at rest. So an object at rest wants to stay at rest. And inertia is a property of matter related to its mass. The more mass an object has, the more inertia an object has. That's why it's a massive mass. All right, so are you ready for this?
Do it.
Is there anyone, how many people think that if I pull this real fast, that it'll break above the mass? Raise your hand. Anyone? Nobody wants? There you go, boom. All right, so he saw it before and he says above. All right? Sam, what do you think?
Bottom.
Bottom string. All right, here we go, real fast. You ready? Top string? All right, she switched, swing vote. All right, so here we go. You ready, Nick?
Yeah, I'm ready.
You ready? Here we go. 1, 2, 3.
Yeah.
All
call
What knot
that.
did you use? Or kind of thread?
It's snapped. Anyway, I'm gonna pull slow. Is it gonna be the bottom string breaking again? Same knot,
No.
Top.
same string.
Top one.
Top one's gonna break.
Yeah.
If I pull slow, the top one's gonna break. Why?
Newton's
Why would-
laws.
Because you're
No.
acting upon a force. on it. Putting a force on it.
Newton's laws.
Because I'm doing what?
You're putting a force on it.
I'm putting a force. I put a force on it before. Now, this was an object at rest or in motion.
Rest.
So when I pull fast, an object at rest tends to do what?
Stay at rest.
So if I pull slowly, then I will do what?
That'll be in motion.
Make it motion.
You want to stay at rest. That's great.
Oh, you got that? Okay. I have here two boxes. I have here a large box, and I have here a small box. Large box and small box. Josh will attempt to give the boxes a whack. 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 You don't touch the boxes. All right, Josh. Don't touch the boxes. All right, so here we have a rubber mallet, we have a volunteer, hold it, and we have a class full of students. If Josh can give these identical whacks, what will happen to the two boxes? It's right here. There's a box, there's a little box and a big box.
Well, it'll get a
Are they
10.
empty?
What will happen to the boxes?
We'll get a dent.
The big one's gonna dent, so I wanna get that less.
And the little one's gonna dent less.
Hooray.
All right,
True that.
would you please give a nice solid, no, stop. Don't, no. Whack with the mallet, they can see it. Give it a nice solid, like, not down, no, like this. Here, let me show you. He's gonna whack it on the side.
Oh.
He's gonna give it a whack on the side.
Oh,
Big
so-
old
Are you ready? Wait. Just a nice solid whack. Don't get too dramatic. All right, give it a whack. Whoa. All right. Same.
Who went left? Like I predicted.
All right. One less like he predicted. So,
Box full of cement.
this box, why did it move less?
Obviously, it had more mass.
inertia.
It had more mass, it had more
Inertia.
inertia.
It had more
Inertia is a property of
lazy.
Mass.
matter. Very good. All right. Good. Oh, one more demo. One more demo.
Room for two?
You okay, Mary? Oh, you didn't? All right, who likes apples?
Me.
I like apples.
Oh, can I do this new?
And fruit.
All right,
Let me do it.
here we go. An object in motion, Sam likes to do what? So if I slam this on the table, what's gonna happen to the apple?
It's gonna break right.
All of it's gonna, we'll keep on and come down, so all of it's gonna break.
Yeah, maybe.
So
Keep wanting to come down.
I'll do it. Well, that way you guys can see, because otherwise I'm standing in front of it. All right, so you ready?
Yeah.
Hold on, Gildy.
You ready?
1, 2,
Do it.
2.5.
Hey! Hey!
What do we eat for dinner?
There you go. Apple for dinner. What's it? Yeah.
Yum. Look at this apple.
Awesome, now it's yours.
It's falling on the floor a couple times.
A couple, yeah.
All right, object in motion remains in motion.
Sir.
Yes.
All right, cut.
Record. There it goes. Record. Yep.
Marble. Ready?
Oh.
Ready to go.
What's the motion of it right now?
Oh, so let it go over
I
here.
mean, what's creating the circular motion?
We're moving the, whatever that is.
Was that a straight line or
That was
curve?
a straight line once it exited circle. It did not change its path.
And why? What does Newton's first law have to say about
Object
that?
in motion want to stay in motion.
What type of motion?
Forward, straight, 9.
Unless?
Unless acted upon outside force.
Okay, thank you.
You're welcome.
Yeah, go straight.
So, what are you gonna do right here?
I'm gonna pull this tablecloth out from underneath the plates and such.
Look on the floor.
And they are going to remain generally in the same place that they were.
Why would they remain there?
Because, according to Newton's first law, an object at rest will stay at rest because it has inertia. And these things are matter, so they have inertia.
And why did you put the glasses on the plates?
To give the plates slash glasses more inertia than they would have had separately.
Now, I saw a famous TV scientist guy do this trick, and when he had the other person do it, he put the glasses on the table, and then when he did it, he filled the glass with water and put them on the plates. Why was he cheating when he made the other guy do it the other way?
Because with when he added the water and centered all of them in the same place, it gave the mass just one big thing.
One biggin?
One big thing of inertia.
Okay, all right. More mass means more what?
Inertia.
There you go.
Ready?
Yep. Whoa. So why did the silverware have the most motion?
Because they don't weigh as much, so they have the least inertia.
Awesome. First of all, how many of those hex nuts do you have on there?
26.
26 hex nuts. And what are you attempting to do with those 26 hex nuts?
Drop them in this bottle.
In that bottle there, from way up here. Well, how are you going to do that? How do you?
I'm gonna snatch this ring out from the center, and they're gonna drop straight
And
down.
why would they drop straight down?
Because the only force acting on them is gravity, and Newton's law says an object at rest will stay at rest, and an object in motion will stay in motion.
All right. So are those objects in motion or at rest?
They're at rest.
So when you pull the hoop out, they will.
Drop.
Before they drop,
They will stay there.
they will stay there and then they'll drop. Okay, let's try. Let's see. All in there. All 20. How many?
6.
6. All right. So what are you attempting to do?
Spin without the book falling.
Okay, let's see. Slowly, 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 slowly. All right, good. Now stop it. Now try to do it real fast. Just turn around real quick. That was good though. So when you turn around the second time, the book didn't move. It stayed like facing. The first time you rotated the book, the second time you moved, but the book didn't. How come?
Because it was at rest and it wanted to remain at rest.
All right, try it this way. Put it on your head and go slowly in one, and then once you do a complete circle, try to spin the opposite direction. See what happens. So slowly all the way around. Slowly, 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 slowly. Now the other way. There you go. Boom. No?
You guys want to see something cool?
Chris, is that really grape soda?
Nope.
No,
What, Jess?
I'm trying to see what
What am I supposed to do with this?
just wait.
All right, you ready? Hey, you guys are gonna miss this, Josh. Come on. Chop chop. All right.
No way. Are you gonna pull that dollar?
Are you ready? Are you ready for this?
Oh yeah,
All right.
Mr. Noon.
Now, Newton told me that if I yank this dollar bill out,
Oh my god.
Pretty cool.
boom!
Pretty cool.
Up it up.
Holy crap.
Can't deny it.
Can I get that dollar bill?
All right, go. All right, so what happened there? Can you describe that motion?
Uniform velocity in a straight line.
All right, so an object in motion tends to do what?
Stay in motion is uniform velocity in a straight line.
Excellent. What's going on here?
Okay.
Does he sit up?
Um.
You just bend him at the waist, right?
No, he's chilling out. Oh, I'm kidding. Okay, all right. Pretty much, this car or bus thing is gonna go at the wall. But when it goes to the wall, the car, that bus thing is gonna stop, but he's not. He's gonna go keep going.
Because an object in motion?
Yep, object in motion stays in motion until an outside force acts on it.
All right.
So I'm going to demonstrate this by hurling this at the wall. Ready?
Yes.
Hey,
Oh.
see, and he keeps going straight because
Yep.
he's in motion. He wants to stay in motion.
Okay.
Now, how seatbelts work. Seatbelts kind of constrict this motion. Because, yeah, the guy's going to still go forward, but the seatbelt is going to hinder. It's going to hinder that force. Like that, see?
Very
So,
good,
This is why
very
you
good.
wear seatbelts when you're in a car.
What happens when you're in a car, like that guy, and you get hit in the back?
The back.
Yeah. So if this guy's sitting in his car, if you could make him sit on the edge like this, like bend his knees.
Alright, let's try to see where that, okay.
All right. So if he's at rest
What does this remind me of?
and a bus comes in and hits him, what's gonna happen?
He's gonna,
What happened to him?
he went back.
He fell back.
Fell back, yep.
Is that what you expected? So here he is sitting here. Here he's just sitting there, and give him a good hit. Whack! Oh, he got not that much, Mary. Oh, Mary, you ran him over twice when you pulled out too. Oh, jeez, Mary. You're just gonna put him in the car and pretend like nothing happened?
Yes.
Oh, Mary.
Yep, but he fell back.
Oh, well, why? What was he doing when he was hit? Was he in motion or at rest?
Well, he was at rest,
So when he got hit, where did he want to stay?
wanted to stay at rest.
And what happened to the car that was under him?
Went forward.
So he
did
went.
not.
So he
Went back,
so he
yeah.
fell backwards. Actually fell straight on the ground. Yeah, add to that.
Wouldn't, because the car has more mass than he does, wouldn't the car have more inertia, thus the car staying in place?
Well, what was the car hit by?
A big
Bus.
truck.
And the big truck has even
More inertia.
more inertia. So the big truck had even more inertia. The car wants to stay in place, but it's whacked. He didn't have a seatbelt on, did he? And then Mary ran him over with the bus too, right? So first he fell out of his car. So what is this? What should that guy who has his arm broken and you still put him in the car to drive home like that? What should he have on also?
A seatbelt. He
If he had a seatbelt on, would he fall out of the car?
No.
No, he wouldn't fall out. Let's try it. You got another rubber band somewhere? Try that one.
Actually, you know what? Let's take Aquaman.
Yeah.
Just take him out.
Let's put a seatbelt on the guy with the broken arm there.
It's not like it's gonna help with anybody.
Oh, jeez. You're gonna have to put it around his lap, man.
It's okay. Shut up.
Well, she'll see a lot of people like this. All right, here we go.
Oh, that's awful.
All right, go ahead and whack him. And did he fall out of the
He goes
car?
back, but he doesn't fall backward.
Excellent. So seatbelts are
Seatbelts are vital to our health.
very good.
They're
Very good.
necessary.
Thank you. What's going on here? Here's a,
I got a stack of compasses on a table, and I'm gonna try to slide this one compass to knock the bottom compass out, but keep the top three in a stack.
why would they stay in a stack?
Because these objects have inertia and they want to stay where they are. So they'll just drop down, remain all lined up, and like so. Objects in motion stay in motion until acted upon by outside force. Objects at rest stay at rest. Science from MrNewton.com.
There you go.
Hey, what does this have to do with the nurse shot?
Science with MrNewton.com.
Was it
Go there. Go there now. Learn science.
Do it again
with this guy.
Stand over here. Do it over here.